Hello, and welcome to this feature of the week video on calculation of exposure metrics in Simulx. Exposure response analysis is an important tool for guiding clinical trial decisions, in particular dose selection and justification. It allows us to determine the relationship between the drug exposure and the drug effect, whether the effect is therapeutic or toxic. But how do we make the connection? It starts with summarizing the drug's individual pharmacokinetic profiles into a few exposure metrics. Then we link the exposure metrics to the drug's effects, study differences between individuals, and then use simulations to improve clinical trial decisions. In this video, we will focus on the first step of this process, that is calculating exposure metrics. These metrics help us describe the drug's presence in the body, so how much, how long, and how it changes, and they are essential for exposure response analysis. Some of the most common exposure metrics include Cmax, that is the peak concentration of the drug in the body, and AUC, that is area under the concentration curve, which reflects overall drug exposure. For multi-dose regimens, we also calculate partial AUC, which is the AUC over a specific time interval, like between 2 doses or daily, and Ctrough, which is the minimum concentration before the next dose. Metrics at steady state, such as Cmax and average steady state concentrations, are also frequently used. These metrics represent the drug's equilibrium, where the amount entering and leaving the body is balanced. This makes them especially useful for assessing long-term drug effects. In earlier feature of the week videos, we showed how to calculate simple metrics like Cmax and AUC directly in Monolix, and then save them using the table output statement. While this works, the values that are returned are only at time points that are present in the original dataset, which in many cases can be inconvenient. For more advanced cases, like calculating exposure metrics over several intervals or merging them with the response dataset, a better option is to use Simulx combined with post-processing in R. So let me briefly explain how calculation of exposure metrics fits into an exposure response workflow. First, we build a PK model in Monolix. Then, we export this model to Simulx to calculate exposure metrics. We can calculate exposures directly in Simulx or simulate time concentration curves and calculate exposures outside of Simulx using tools like R. Finally, we merge the exposure metrics with PD or response data and then use them to build the exposure response model in Monolix. In this video, I will show you how to calculate exposure metrics with a few examples. First example will be when we want to calculate exposure metrics in a single time interval. Then, in 2 intervals, then we will calculate exposure metrics over several intervals, like interdose or daily, that can be common or specific for each subject. We will look at typical metrics like Cmax, C-average, Ctrough, and AUC, and I will also show you how to merge the calculated exposures with PD data. Before we get started, if you're new to Simulx, I recommend checking out these 2 videos. One on a typical Simulx workflow and other on using the built-in outcomes for easy post-processing of simulations. While you don't need to watch them to follow this tutorial, they will definitely help if you're just getting started with Simulx. In this video, I'm going to use a simple example of a drug targeting PCSK9 to lower the cholesterol levels in the blood. I have PK data showing the drug concentration over 6 months and response data, which is the change from baseline in LDL-C levels. My ultimate goal would be to perform exposure response analysis using exposures derived from model predicted concentration time curves. Let's take a look at the PK data and the PK model that I've already developed. The dataset includes 50 individuals who received 12 doses, 1 dose every 2 weeks, over a 6-month period. Sampling is dense after the first dose, and then for the rest of the study we mostly have Ctrough samples. At 6 months the drug concentration is at steady state. In my Simulx project, I've already built and estimate PK model. The standard errors of the parameters estimated are within acceptable ranges, and the VPC and individual fits show that the model fits the data well. To calculate the exposure, I will use the predictions using the individual parameters as we see in the individual fits. I can calculate the metrics on any interdose interval, even if there are no observations in that period. The response data in this study, that is change from baseline of the LDL-C levels, was also collected up to 6 months. And I'm going to use subsets of this dataset to explain the workflows of exposure calculation in 3 different cases that I mentioned before. So in 1 single interval, in 2 intervals, and for interdose interval. First example, exposure metrics in a single time interval. In this case, I consider that I have only 1 response value per individual at time 168. And I want to link this response to the exposure metrics at steady state. So let's go back to our Simulx project with PK model. To be sure I have reached steady state for all individuals, I will use the interdose interval after the last dose. Cmax, Ctrough, and C-average at steady state can be easily calculated using post-processing in Simulx Outcomes and Endpoints module. To calculate those exposure metrics, I start by exporting this Simulx project to Simulx. The model, parameters, and treatment have been imported from my Simulx project. In the Simulations tab, I switch the parameter from MLX-POP to MLX-EBEs. This is because I want to simulate the individuals from my original study, not a new population. Note also that the MLX-ADM is selected by default, which allows to resimulate the original treatment regimen. In Simulx, the first step is to define a new output element. I use model predicted concentration of a drug, which is L-tot in this case, on a regular time grid from 154 to 168, which is last 2 weeks of the observation period. And I'm going to use a fine grid with 0.01. I'm going to call this output concentration steady state. And now I add this to my simulation scenario in the output section. Next, I create an outcome based on this new output element. So in the outcomes and endpoint section, I create new outcome. I call it Cmax at steady state. The output variable is selected by default, and I use post-processing as max per ID. I click OK, and in the same way I'm going to create also Ctrough and C-average outcomes. So I create C-average at steady state with the post-processing average value per ID, and Ctrough at steady state, which is last value per ID. Note that in this case I could also use value at a custom point per ID and select 168. For AUC, the calculation requires a few additional steps as it is not directly available in the post-processing menu that we have here. So to compute AUC in Simulx, I add in the model definition additional lines, and this I can do with the option add lines. The computation of AUC in Simulx follows the same MLxtrans syntax as in Monolix. So to calculate cumulative AUC, I will add two lines, AUC_0 equals 0 to initialize AUC variable, and DDT_AUC equals LTOT to define the ODE equation. This will integrate the concentration profile LTOT from the start to a defined time point, and this time point will be specified in the output element. Now, to compute AUC between two specific time points, T1 and T2, I use an if-else statement that calculates first AUC from 0 to T1, which is defined here, and then from 0 to T2, which is defined here. The partial AUC for the interval from T1 to T2 is simply the difference between these two intervals. In this example, T1 is 154 and T2 is 168. Now I click apply. Then I create an output element with my new variable AUC. These variables are available in the intermediate outputs menu. I call it AUC steady state. And instead of using a regular time grid, to reduce the computational cost, I will use the manual method with one time point at 168. Now I add this output to my simulation scenario, and I'm going to create an outcome with it. So AUC steady state. No post-processing is required in this case, but with an outcome that is equal to the output, all my metrics will be in the same result folder. So once the setup is complete, I save my project. And I run the scenario. The results include dedicated plots for each outcome and are also presented in the Results tab in the Outcomes table. However, in this case, I'm more interested in the output files in the Results folder that I can access from here, because I need to merge these results with my response data. They are located in the endpoints with the file starting from outcome. Merging can be done directly in Monolix using the data formatting module. Data formatting in Monolix allows to add information from external files to a dataset for analysis without modifying the original dataset. There are two important rules when doing it. First, the file you want to add can have only one value per individual. For example, it can be constant in time exposure metrics at steady state. Second, the response dataset and files with exposure metrics must have the same number of individuals and the same subject identifiers in the column ID, like in this example here. When it's not the case, so when ID in your response dataset is not an integer from, for example, 1 to 50, but a custom number or a string, then you cannot add Simulx outcomes files directly in data formatting module, because the ID columns must be the same between these two files. But Simulx output files have two columns with ID. Simple ID header is for simulated IDs. They are automatic sequential integer numbers for simulated subjects. However, there is a second column called original IDs, and this column includes specific identifiers used in simulation elements, for example, in a table of individual treatments or a table of individual parameters. These original IDs are reported in the outcome result files, like in this example, or as a separate file. To use data formatting module in this case, you first need to modify the outcome files outside Monolix by removing the column with simulated ID and renaming the column header from original ID to ID. So let's go back to Monolix. I start a new project and I'm going to load a dataset with the response measurements, where I have only one measurement at time 168, via data formatting. In the initialization step, the ID and time columns are automatically mapped. At the next step, I select an observation, which is response column. And in the additional columns tab, I browse my result files with exposure metrics that I have in the results folder of my Simulx project. Here I can add additional files for other exposure metrics, but as this is just a demonstration video, I will stop here. I click on Preview. Now we see that the columns that were found in the external files are tagged either as regressors or covariates. I need only the exposure metrics as regressor because I will use it in my exposure response analysis in my structural model, so I keep this one and I ignore other columns that I'm not going to use them. The baseline column can be also tagged here as continuous covariate, and I can continue with the exposure response analysis. But the exposure response analysis is not a topic of this video, and if you want to learn more, please check out our feature of the week video number 85 on modeling exposure response curves in Monolix. Now let's go to the next example, in which we would like to calculate exposure metrics in 2 time intervals. So here I have a response dataset with 2 measurements per individual. One is at the end of the first dose interval and second is at steady state. I want to now link those responses with the corresponding metrics. So let's go back to my Simulx project. When we need to calculate exposure metrics over more than 1 time interval, but still not too many intervals, the process is straightforward. We simply add new output elements in Simulx with the corresponding time limits. I already have here exposure metrics at steady state, so I need to add one that is on the first 2 weeks, so the first interdose interval. So I'm going to create a new output for the concentration, which I can call concentration at 14 days. I use the same output and I use a time grid from 0 to 14 with a time step 0.01. I add this output to my simulation scenario and I create a new outcome, which is Cmax in the first 14 days with max per ID, and I can repeat this process for other metrics like Ctrough and Caverage. The same is for AUC calculation, so I already have in my model calculation of AUC from 0 to sometime t, which is here. So in the output, I'm going to create a new output element with the manual method, and now the output will be at time 14 with name AUC 14, similarly to what we did for concentration, with the output AUC from 0 to t, so it will be from 0 to time equal 14. And as previously, I add this to my simulation scenario and I create the outcome as well. Now I save my project with a new name let's call it simulation 2, and run this scenario. When I have several exposure metrics at different times, as in this example, we cannot merge the results with the response dataset using the data formatting module in Monolix, as I showed you in the first example. To handle this, we can merge the output files from Simulx with our response dataset in R. This R script will merge the outcome files that are located in the endpoints folder of my results folder of the Simulx project with a response dataset into one file. For simplicity, I included time points in the outcome names such that the script can extract those time points from the file, then reshape the data and then merge it with the existing response dataset. If I open any of the outcomes file, we see that each file contains common columns like ID, original ID and group, and specific column like here AUC_168 that we want to merge with the response dataset. This script will create new columns in my PD dataset, in my response dataset that I load here, and these columns will be AUC and Cmax, as these are the metrics that have been detected in the endpoints folder. So this code will work also with any number of files that you have in the endpoints folder and with any time points whenever you include the time in the outcome name. You can download this script with other materials for this video in our documentation page that I will indicate at the end of the video. Now let's look what is the result of this code. We have a column with response, which comes from our original dataset, and two additional columns, AUC and Cmax, with values at 2 time points that were calculated in Simulx. Note that exposure metrics can be available at time points where no response measurements are present. For example, if I don't have a response at time 14, but I have metrics at time 14. In this case, you can just leave a dot in the column with the observation. Conversely, if there are response measurements without corresponding exposure values, for example, for ID equal to, I have a response measurement at time 14 and 168, but exposure only at time 14, then as in previous case, I can use simply dot in the exposure column. Monolix can handle this automatically by applying either last carried forward or linear interpolation method for the missing exposure values. And the R script that I just presented you includes these two cases. Note here that as AUC and Cmax might be used as regressors, you need to have a value of the regressor at the first time point of the observation or of a dose for each ID. Now let's move to the third example when I want to calculate exposure metrics in several time integrals. I want to calculate exposures for many intervals, such as each interdose interval over a long period. It can be also daily exposures, weekly exposures, monthly, and so on. For this purpose, using a script in R is more efficient and flexible than doing it manually in Simulx like we did in previous example. So let's see how to do that. In this case, I'm going to use a PK model built in Monolix to simulate in Simulx a concentration profiles and AUC on a fine grid that will cover the observation period of interest. Previously, we used Simulx to calculate directly exposure metrics. Now, we will simulate only PK profile and AUC. Then I'm going to read the results of the simulation in R, calculate exposure metrics, and then merge the results with the response data. This method is highly flexible and it allows us to define the interval length, different number of intervals, and even use individual specific intervals if needed. So in this example, I want to calculate exposures for each dose interval, which corresponds to 2 weeks. I already prepared a Simulx project with a simulation scenario. If we look on the output, it generates concentration and cumulative AUC values over a fine grid starting from 0 up to 6 months. Note that I calculate AUC directly in Simulx on the same time grid, using the same approach as in previous examples. While it's possible to calculate AUC also in R, Simulx uses an ODE solver and efficient C++ code, so it can provide greater accuracy and efficiency than, for example, the trapezoidal rule in R. So after running the simulation, we will switch to our script that will use the results and calculate exposure metrics for custom intervals. This code is also available to download on our documentation page. Here, we are going to read as previously files that are in simulation folder of our results of Simulx project. Then we define a time intervals in which we want to calculate exposure metrics. Either it can be the same time interval for each individual, like every 2 weeks, or you can load a text file with a column ID and column time where you specify individual specific time intervals, and one of the examples is the MLX ADM file which you have in Simulx when you import a Monolix project, and it corresponds to the dosing of your original design. In this code, we have different functions to calculate Cmax, Ctrough, Caverage, and AUC. Here, the partial AUC is calculated as a difference in AUC value between different interval boundaries. Finally, the output is combined into a single file with columns ID, time, AUC, Cmax, Ctrough, and Caverage, and then is sorted by ID and time. The final file is saved as CSV and can be merged with the response data as demonstrated in the previous example. In these 3 examples, I calculated exposure metrics based on the original design and individuals from my original study. However, this workflow can be extended to simulate new scenarios. This procedure must be done at 2 stages. First, I create a Simulx project with the PK model, and then I use it to simulate PK time concentration profiles of the new scenario, and then I calculate exposure metrics in a similar way so that I presented you in this video. Then I use the exposure response model in a second Simulx project. Here, exposures will be treated as regressors in a Simulx project and defined using external files generated during the first simulation. And then I can simulate a response based on the calculated exposures. Thank you for watching this video, and I hope that these examples will help you to make your exposure response analysis easier and more efficient. Feel free to check out our documentation page and download the materials and R scripts from this feature of the week video.